So last class, we introduced the concept of ordinary least squares regression. And for me, OLS regression is sort of like the magic. And it's the magic of taking all of this data, this cloud of data, and finding a special magical line. To take a cloud of data and turn it into the magic line. And why is the line magical? Well, the line is magical because it represents the best, unbiased, linear estimate of this relationship. The relationship between x and y. It happens to take the form of a slope, which again, flashbacks to high school. When you have the slope of the line, when you have a 1 unit increase of x, you get how much of an increase in y. Insert question mark there. How much of an increase in y are you going to get? Huh? Y1, Tom. So what is that? What does that 1 represent? Wait, let me do this one more time. Okay? When we have a slope, any slope, a 1 unit increase in x corresponds to how much movement in y? Not always. Without numbers, use words. How much does y increase? By whatever number the what is. By whatever number the what is. For a 1 unit change in x, you get a blank unit change in y. But the blank is a word, not a number. No? Sending you all back to high school math. And you'll pay attention there because you'll have a greater appreciation for it. Okay, you won't, but at least I'll feel better. It is linear. But how do we know how much y increases? What is the value of that blank? I have 2 acceptable answers. I'll think of one of them really hard right now and see if one of you can read my mind. Got it? No. Okay. Okay. A 1 unit increase in x equals whatever the slope is, increase in y. It's not a trick question. I would have accepted beta. And then you were like, I wouldn't have gotten beta. Okay. Oh, I'm exhausted. Can we take a break? I was thinking so hard. All right. That's the beauty of the line, right? It's linear, and so therefore any increase in x of 1 unit gives us a beta unit increase in y, or whatever the value of the slope is. And in high school, when you did mx plus b, it was the m. That was the slope, right? Somebody just nod. Yeah, right? I remember that. Sure. Prom sucked. But I remember that. Okay. Yeah, it did. All right. Or, now that we're doing ordinary least squares regression, our y equals mx plus b is now slightly different. Y equals beta 0 plus beta 1 x1 plus e. So what is the slope of the line for x in this instance? It's that beta 1. Okay. So what we're doing with ordinary least squares regression is two things. One, we're figuring out where to put the line. And two, we're getting a measure, a coefficient, a statistic that represents the relationship between x and y. Okay. That's what this beta 1 does. It represents the relationship between x and y. And it represents the direction of the relationship. So if it's positive, we have a positive slope. All right? So this is a positive beta. If it's negative, we have a negative slope. And what happens when you have a zero slope? How can a number be neither positive nor negative? When it's zero. See? Zero slope. Okay? So if our beta comes out to be 0, that means a 1 unit change in x has a 0 unit change in y. Why? Because there's no relationship between x and y. There's no relationship between your independent variable x and your dependent variable y. When I was in grad school, I spent summers at the University of Michigan taking statistics classes, and it's long, it's the summertime, and you're in a basement of some building for 3 hours learning stuff way, way, way uglier than that equation I showed you earlier. And I'm taking a class on, what was it? It was Bayesian statistics. Stuff that, again, we should send Bayes textbooks down to Gitmo if you want to torture some terrorists. Bayes is just horrible. Not a number to be found anywhere, and some upside down signs. Bayes is horrible. And we're talking about model fit, and some guy's like, you know what? Scottish women's unemployment. And we're like, what are you talking about? And we're so exhausted from the class and the heat and everything that became the joke of that class for that summer. Scottish women's unemployment. Well, have you tried Scottish women's unemployment? As a variable. Now, what would Scottish women's unemployment rate have to do with anything that happens in America? I don't know, but it's information. So if you want an example of what's something that should have a 0 slope, Scottish women's unemployment is my example. Because if you're studying why Americans spank their kids, Scottish women's unemployment should have no impact on whether or not somebody thinks they should spank their kid or not, right? The birth rate in regions of the United States, Scottish women's unemployment should have no impact on that, right? This is the most absurd thing we could think of as a concept that you could collect data on, but man, that better not have any relationship to what it is you're studying. So if we were to put Scottish women's unemployment into one of our models, I hope it would come out as 0. Okay. If you haven't put this in your notes yet, go ahead and do it, because I want to walk through an example. And I'm going to need you guys to have this. All right, so beta 1, you can make it a big B. So I don't know why this is a little b. Is the sum of xi, that's a subscript I, minus x bar divided or multiplied then again by yi minus y bar over the sum of xi minus x bar squared. And then beta 0, which is our y-intercept, is y bar minus beta 1x1. Okay, that should be a big B. This is what I was going to give you for homework, but I don't want to because I'm nice, and it's the end of the semester. This is more of a beginning of the semester kind of assignment, where I don't mind if you spend hours working on one equation. All right, here's what we have. I have data on birth rate and income. We're going to ignore the percent African American for this example. Birth rate. So how many babies are born in a year per 1,000 population? And then we have the income per capita measured probably in 10,000s of dollars. Yeah, it's got to be higher than that. There must be a zero missing. A lot of times we reduce things down to get rid of the zeros because, well, you'd make a lot of mistakes if you had more numbers, right, Ryan? Okay. So what I was going to have you do was use this equation here, number 3, to calculate the beta for 2 different lines. One for the per capita, income per capita line, and one for the birth rate line. But again, it's the end of the semester and nobody wants that. So we're going to stick to finding the relationship for income just by itself. Okay, so let's do that. Let's take this data and pop it in here. Let's make it just a little bigger. Okay, you can see that, right? Which one is our dependent variable? What is the phenomenon we're trying to explain? Would we try to explain birth rate, or would we try to explain income? Birth rate. Why do you think birth rate is the good dependent variable here? Yeah, because that's what I said. How would birth rate influence income? So how does the fact that people in my region have kids affect the wages that we pay? Anybody want to come up with a theory for that? Okay. Okay. So the idea behind it, as Tom said, would be that having kids would require you to work. Right? There's actually studies that look at the pay gap between men and women, and it turns out men, I'm sorry for this, ladies, men actually make more money when they have kids. So, gentlemen, keep having kids and your pay should go up. Women, when they have kids, their pay goes down. So the fact that I have 2 kids, for some reason, in settings, men's pay tends to go up the more they have kids. Just a weird thing. Okay. So we're going to have the birth rate be our dependent variable, and income is going to be our independent variable. All right, so that big nasty equation that we have. Is that it? Come on, you gotta be impressed by that. All right. So what would we do? If we're gonna bucket on the floor of this equation, what do we need to do first? We gotta what? All right, so find the mean. Somebody get out your calculator, your phone. Somebody handle y, somebody else do x. Ladies do x, gentlemen do y. There's 9, I'll give you that. N equals 9. Okay. Who's got one for me? Guys are taking forever. Y bar is what? Okay.
573.5.
Okay. So now we have our x and our y bar. What would we do next?
You gotta use the formula x1 xi minus x bar.
Okay. So the first thing is xi minus x bar for each one. Okay. So x1, 39.98 minus 35.70, let's call that 4. $39.98 minus 35.74. I got 424. Did somebody else get that? Y'all are writing and looking down. Did anybody actually doing any work?
What you said?
That's what I got.
That's what I got.
Okay. Now, what is that number? Let's take a step back. What have we just calculated?
X1 minus x bar.
Yes, but what is that? How can we describe what that is?
The variation between the mean and the variable.
Okay. When we think about the data, we have our observation, we have our expectation, right? Our average. So what we've calculated right now is that distance between what we have observed and what we expect. We expect that the average is going to be the mean. Okay? So what we're doing when we're going through this is we're calculating how much that gap is between what we observe and what we expect. So we're going to go down through and we're going to do that. What's the next step? We're going to do the same thing for y. Okay. So 22.5 minus 24.34. Negative 1.84. What do we do next? We go down through and we do that for all of them. Now, next we're going to multiply them. So what is negative 1.84 times 424? Minus 780.16. And then we're going to go down through and we're going to do all of those. What's next? Okay. You're going to do x of I minus x bar squared. $424 times 424. And this is when you start cursing me, because now you're like, oh, this is a lot of digits. This is going to be a really big number when I do this 9 times. And add it all up. Okay. How long do you think this would take? 30 minutes? Yeah, probably. This is a program on your computer called SPSS. And if you're listening to this video, it's not going to make any sense to you because I switched computers. You just have to trust me. Here's what I did. You have this on your computers here in the lab. I typed in those numbers. And I need to analyze this data. And I know it's a regression. I know it's a linear regression. And it lists the variables. And I put them as the dependent variable and the independent variable. And I said, okay. And in the time that it took to go from that window to this window, it ran the analysis. OLS regression is probably the last thing in a statistics class that I can teach you how to do by hand. Anything after this, you have to do on computers, and you have to use statistics software. So you guys this semester have been given a set of skills that you can do by hand to test for differences of means, to look for differences of proportions, to look for like a chi-squared to see if there are differences among categories. But if you want to build a model, this is about as far as you can go by hand. Right? You can continue to go on through and calculate all of this, and when you sum these things up, you plug them into the equation. but you're going to hit a spot where now I need to do this by computer, and I need to do it quickly. So what do we have? What results are given to us? Well, the first thing that we want to look for to understand is that beta, right? Because that's what we were trying to compute, right? We're trying to compute the slope of the line. The slope of the line, we're given 2. We're given 2 betas. The constant, right, which we think of as the y-intercept. The constant, beta 0, is 31.56, and our beta 1 that we were just trying to compute, negative 0.002. So what does that mean? What does that 0.002 mean? For a 1 unit increase in X. So for every $1 increase in the median or the per capita wage, you should expect to see 0.002 more babies per 1,000 live births. You don't think so? You should see less. I'm sorry, less. So as income goes up, what happens to births? They go down, right? Because the negative sign. Okay. So is there an impact, right? Is there what we think is a relationship between X and Y? Yes, but it's kind of small. Why is that number so small?
Because of situations on both sides.
What do you mean, the situations on both sides?
Well, because it depends on the individual. There are situations in which having more money would make a person have less children, and situations in which having more money would make them.
No, absolutely not.
So
Why is that number so small? I'm going to smirk a little bit so you know it's a smart-ass answer.
because regardless of how much money you have, you still have sex.
No. No. Why is the impact of income so small, or have such a small impact on birth? 0.002 negative. George? And we'll get to that question next. Why is that number so small? Because we kind of made a little bit of a, I don't want to say a mistake, but we overlooked one really important thing. When we interpret that number, how did I say it to you? With a blank increase in X, with a blank increase in income. What is a 1 unit increase in income? How much?
$1.
$1. Do you notice $1? If you open up your wallet and you have $52 versus $53, do you notice that? You open up and notice when it's $0, right? And you know the difference between having $3 and $53, but you don't really notice the difference between having $3,399 and $3,398, right? So the scale by which we're measuring income is really small. Right? There's not a huge amount of difference in some of these variables. So when we look for the impact of X on Y, and we're measuring it in thousands of dollars, or however it is that we're doing it, we're going to see a really small impact. So should we pay attention to the size of the coefficient? No, we shouldn't pay attention to the size of the coefficient. Why? Because it all depends on what? The blank of your blank. Yeah, the unit of measurement of your independent variables. Okay? So we're not interested in the size of the coefficient. So what should we be interested in? We're not interested in the magnitude of the effect. When you say correlation, what do you mean? Okay, so what sort of relationship does income have on birth rate? Negative relationship. So what are we paying attention to when we look at that number? Let's go back to the number. What is the number? Whoa. Right. What is that number? It's negative, so it has a negative slope. So that's what we're interested in, right? We're interested in the direction of the relationship. Aaron, what question did you ask? Why do you think there's no correlation? All right, why does it, you said a magic word, you're just doing it wrong. What do you mean insignificant? Tell me what you meant. Yeah, the number's really small, but I explained to you that that reason is because we measured income really strange. But you're right. When you're questioning whether or not it's significant or not. What do you mean significant? What do I want you to mean when you say the word significant? We kind of, in introducing OLS, we kind of forgot the process, right? Remember how when we were doing the last few homework assignments, what are we really testing here? Yeah, I haven't mentioned anything about the null hypothesis, have I? Go back. So let's think about this for a second. Okay, that'll work too. All right. We're talking about the relationship between income and birth rate. And we have a theory that they are related, that a change in income will influence the birth rate. That's our alternative hypothesis. What is our null hypothesis? But how would we represent that, given what we've just talked about, given this ordinary least squares framework? How would we represent no relationship between x and y? Zero slope. Okay? So the null hypothesis is that there's a zero slope. Or that beta 1 is 0. Okay? Our null hypothesis for ordinary least squares is the idea is that there's no relationship between your independent variables. If we're using the beta to represent the relationship, and we're measuring it by, to some degree, the magnitude of the effect. So what Aaron said is, that number looks really small. Well, the number matters. It matters, first of all, whether it's positive or negative, because that would seem to indicate that there is an effect. But also the number matters not because the 0.002 was small, but that it was so close to being 0. So our alternative hypothesis is that beta 1 does not equal 0. What's our decision rule? Here's our beta. But now we need a probability. What is the probability that the real beta is not 0? Or said another way, what's the probability that this sample beta is observed in a population where the true beta is 0? SPSS labels it as significance. 0.059. So if our decision rule is 0.05 and we have a 0.059, can we reject the null hypothesis? No, you can't. All right. You'll notice that it gives you the t value. Right? Our t and our z, it actually gives you that value. If you scroll up, the computer also gives you, in the ANOVA table, the degrees of freedom. Okay. So with 8 degrees of freedom and a t-value of 2.258, you would not be in that critical area where you could reject the null hypothesis. So the stuff that you've already learned, we're still going to use. But now we're going to shift our focus a little bit. When I do research, I honestly only look, and I run a model, I only look at 2 things. The beta, what the number is, because I want to know what direction it's in to make sure it fits my hypothesis, and the significance. Because the significance tells me whether or not there's enough evidence in my data of a difference to say that there is a relationship between x and y. Okay? So when you shift to model building, what you end up doing is letting the computer do all that work that you spent all semester doing by hand. But now you truly understand what the coefficients are. It's the slope. And you understand why we have to check for the t or the z and its level of significance. Because now we have to know how likely is it that we observe this beta when in fact beta is 0. Beta 0 is at the middle of your normal distribution.